Welcome to Maths with Bob. Today we're looking at mechanics, circular motion in the horizontal plane, and in particular circular banked curves. Okay, normally applying to roads, but aeroplanes can bank as well. But we are in particular looking at banked road surfaces actually. And if you have a look here, I'm going to just try and see if this magic pen will sort of do let's see if it does it. Ah, yes, it does actually. Okay, so basically you can see here that the friction force in this case is actually acting up, and there's lots of thetas everywhere. The curve is actually banked at an angle theta. We've got a centripetal force acting towards the center of the circle. We've got a normal reaction, and in this particular case, the friction force is actually acting up the bank curve, and you can see this would actually just mean that we are traveling at a speed which is actually not the optimal speed. Basically, we need to, if it is the optimal speed, it would in fact be zero friction. Okay, and if we're going too fast, the friction actually acts in the opposite direction. But so basically, what happens is that when we go around this bank curve, there is actually what's called an optimal or ideal speed for that particular angle, and we're going to try and find that and resolve all these forces. But generally speaking, what happens if we go too fast, we tend to slip up the surface, and friction needs to sort of act down, and if we go too slow, friction needs to act up. Okay, basically, so friction will start to change direction. Now, we're just going to have a quick look at what's actually happening. Okay, well here we have GeoGebra 5. I've set up a little banked curve. Let's just have a quick look at it. Let's see if we can actually rotate it. So just quick look. You can have a look from the top. Okay, the side, bits and pieces. Okay, just having a bit of a look around. This is our bank curve. We can turn it around. I'm going to take out a few things. Let's actually just take out a couple of things. Okay, let's actually just start it up and see what happens. Okay. So here we go. We're going round and round on this bank curve. Let's actually just stop this for a minute. Okay. Now, what's actually happening? Well, we have a centripetal force acting towards the center, mv squared on r, which is the weight. The p is supposed to be a little car. There's a normal reaction to the surface, okay, of the bank, obviously at right angles to the surface, and there's a frictional force F in this case acting up the bank, and this would be, as I said before, this would be a situation where we're actually traveling at not the optimal speed, a bit less than the optimal speed. Okay, but basically this is the situation. We're going round and round here. We're going on a circle. You can see here the actual radius r is a small r there, and obviously that centripetal force is always acting towards the center of that circle. Okay. Okay, well, let's start resolving these forces. Now, we're going to resolve vertically first. Just see if I can. Okay, vertically. So vertically, here is our vertical plane. Now we have to resolve them. The normal, you can see here, the normal coming through here through the angle theta is n cos. The friction is coming through the complement, so it's n sine. So it's f sine theta plus n cos theta is equal to, what else is acting in that direction? Well, you can see here down here, see the weight down here, mg. Okay, now, so basically that's the first equation, and the other one, obviously, we will resolve horizontally. Here we are, horizontal. Obviously, we've got the overriding net force, which is mv squared on r. Okay. So basically, the other components have got to add up to this. Now, let's have a look. See if I can get the pen to work. Okay, I'll just try and. Okay, so I'll just see if I can get the pen to sort of work. Okay, here we go. Alright. Okay, so the pen's going to be working. Good, fantastic. Okay, so here we have. Now, what do we have? Well, mv squared on r is acting towards the center of the circle. Okay, you can see here the angle bank theta. Okay, so that red line is the actual banked curve. And you can see here we've got f coming down through the angle, so we've got f cos, and we have n coming through the complement of the angle, so it's n sine. Now, the trouble is, obviously, one's acting towards the center, one's acting away from the center, so we have if we take acting towards the center as the positive direction, we have a quick look over here. We have n sine theta minus f cos theta is equal to that centripetal force, mv squared on r. Now, okay, if well, f is equal to 0, okay, then we basically can just knock those terms out, and we can divide it 1 by 2. Actually, it's 2 by 1, and we get mv squared on r on mg, which gives us tan theta. Okay, so which is v squared on GI, you can see here. Now, you can see it's independent of the mass, actually. Okay, so the masses have cancelled. Okay. All right, so basically, you can see here, I've actually labeled this V0 for the optimum speed. So if there's no sideways slip, the optimum speed is this one here called, well, V0, which is actually the square root of GR tan theta. Okay. All right, so you can see here, we can just rearrange that. And if you basically multiply 1 by sine and 2 by cos and subtract, you'll end up getting that we have an expression for F, the friction. Okay, and we know that V0, well, I'm back over here, if you rearrange this one here, you can get that V0, or the optimum velocity squared on R is equal to G tan theta, and you can sub it into here for G tan theta, and you can get F is equal to, you can see here, M cos theta on the optimum speed velocity squared on R minus V squared on R. Now, that's just, that's the velocity compared to the optimum speed. Now, if depending on whether V, you can see here, if V0 is less than V, then F is negative, and if V0 is greater than V, then F is positive. That means if we're going, I suppose, slower than the optimum speed or faster than the optimum speed, the friction would actually change direction. Yes, the friction changes direction from pointing up if it's slow, or pointing down if it's actually going too fast. Okay, so basically these, I mean, you can, I'll just go through the, you can actually do this as well, resolving. You can see here, I'll just actually show you, basically you can actually resolve also normally and tangentially. So I'll just sort of show you basically, let's have a quick look. Normally to the plane, that red line, and tangentially or along the plane. So we're going to resolve okay, the forces in these directions now, as opposed to horizontally and vertically. So let's actually have a look at this then. Okay, we'll go through this and try and get the pen to work. Okay, here we go. Let's just see if we can get the pen. We'll get the same equations, obviously. It's just okay. Just try and make this a bit bigger. Okay, all right. So what do we do first when we're doing this? Now you can see here. Well, we've got now the centripetal force mv squared on r actually has components. You can see here there's a component normally, okay, up here, and there's a component tangentially down here. Okay, so we've got obviously mv squared on r cos theta through the angle here, and mv squared on r through the complement of the angle here. So that's mv squared on r sine theta. Now, what are these equal to? Well, you obviously can see here that if I go normally, well, we just have n. N is normal. Okay, so, and what about, yes, down here mg has a component which is acting obviously in the opposite direction, so it's mg, and it's going through the angle here, theta, coming back this way. Okay, so it's going to be, this is going to be the equation here. That, okay, if I go through doing it normally, I'll get mv squared on r sine theta is equal to n, taking obviously the up direction, or is positive, and minus mg cos theta, which is the weights component, if you like, basically normally. And we do the same thing for tangentially, mv, okay, so where's that coming through here? So this is coming down here, so mv squared here, this is the centripetal forces component tangentially. Okay, you can see here there's F is actually obviously in the opposite direction, so it's going to be minus F, and we're going to have the weight mg's component, which is mg through the complement of the angle, so it's going to be sine theta, so mg sine theta. So these are the two equations. If you have a look over here, we have mv squared on r cos theta equals mg sine theta minus f. Now, obviously, if f is 0, we have no slight slip, and we basically, again, we go through this procedure of trying to eliminate n, basically, and basically, well, if we can do a couple of things here, we can get n here and sub n into this one and rearrange, and eventually we'll get that v squared equals gr as before, and say the optimum is the square root gr tan theta, which was the same as we had before. Okay, and again we go through the same process, and you can see here we have the same equations. So it doesn't really matter. We normally would do it tangentially, well, I should say horizontally and vertically. Most people do it horizontally and vertically, but you can actually resolve tangentially and normally as well, and you'll get the same results. Okay, now I guess I shouldn't go past friction, because friction obviously is a very important part on these bank curves, and you can see here that mu, this little funny Greek letter here, f equals mu n, you may have seen this before. Mu is called the coefficient of friction, okay, and the coefficient of friction can be greater than 1. It just means that the friction is stronger than the normal force, f equals mu n, and but normally, I guess you can say the coefficient of friction is actually usually less than 1, and you'll see in the example, I let it be 0.48 for the tyres on the road. Now, basically, I go through these equations, oops, that didn't work that time, with using this f equals mu n here. It's not, it doesn't seem to be working. Just try it again. That basically it's supposed to. Okay, so it gave me. Okay, my circles are not too good. Okay, alright. Okay, how about that one? Yes, here we are. Alright, F is equal to mu n. Okay, this is the relationship between obviously the frictional force and the normal reaction, and mu, the coefficient of friction. Basically, what happens, I'll just show you here. I go through obviously our original equations, and we just let f equals mu n, and then we just get an expression for n. Okay, we do the same thing here for horizontally, let f equals mu n, and basically we just get two expressions for n, and then we equate them. We equate the normal reactions, and then we eventually get that v squared is equal to gr tan theta minus mu on 1 plus mu tan theta. Now, this is actually assuming that the velocity we're traveling at is actually less than the optimum velocity. You'll see that if we do it where the f is acting down, we end up getting v squared equals gr tan theta plus mu on 1 minus mu tan theta. You see the signs are changed around, and we're going to need this expression basically for our example. So basically this is actually an expression for the optimal velocity if we know the coefficient of friction, and obviously the angle and the gravity we're taking as 9.8 meters per second as usual, and the radius will obviously depend on the radius of the curve we're in. Okay, so this is just quite a useful little expression for the velocity there. Okay, now we'll just go through an example. Okay, so we're going to want to negotiate a curve of radius 600 meters, banked angle 20 degrees, and a coefficient of friction between the tyres and the road about 0.48, which is actually quite conservative. It's probably more like 0.6 or 0.7 or something. But I just picked probably a very conservative, if you like, coefficient of friction. Now, the idea is that obviously I'm just going to jump straight into this one here, which is the optimal velocity here. You can see here. This is the optimal velocity for a particular banking of theta and a radius of r, and we used gravity 9.8 meters per second, which I actually should have mentioned there somewhere, but we just assume gravity is 9.8 meters per second. Okay, and we just pop it in and just have a quick look at, for our particular curve, what is our optimal velocity. Now, you'll notice we don't actually use the if you like, the coefficient of friction. Okay, but we end up getting a velocity for this particular a banking of about 46.26 meters per second. Oh, you can see quite quick, 166.54 kilometers per hour. Okay, that is the that's the optimum for that particular banking where there's no sideways slip. Okay, there won't be any sideways slip. Now, okay, so if we want to compare it with the maximum speed, now we'll assume the maximum speed is obviously greater, and this is why we have to use this particular expression with the plus on the top and the minus on the bottom. Okay, because obviously our maximum speed is going to be greater than our optimal speed. Okay, and if you plug all this in, you'll see that our velocity, for our maximum velocity for the particular curve is going to be about 77.54 meters per second, which is about nearly 280 kilometers an hour. Okay. Now, if I obviously increase my coefficient of friction to about 0.5, 0.6, 0.7, that speed gets a bit, our maximum speed actually increases quite dramatically, up above 300 kilometers per hour. Okay. All right. So let's actually have a look at some normal little examples with our no slip situation. Okay, a car is traveling around a bank curve, let's say 15 degrees, radius 500 meters, and finding the safe velocity. Now, obviously, the safe velocity it's fairly easy. I mean, I'll just go through it here. I mean, before you can see here, I jumped straight into that formula. V squared equals gr tan theta. Okay, but I'll just go through here, basically deriving how we get that. And you see f is 0, so I'll just put in 15 degrees. And you can see here the equation 1 and 2. I'm just going to get the pen going again. Okay. Alright, so equation 1 and 2 here. Okay. Alright. So f is 0, you may need to look back at those other equations, but obviously if f is 0, it wipes those terms out. And we look at horizontally and vertically, then we divide these two equations. And then we get an expression for tan theta is equal to v squared on 500g, and we rearrange this to get the speed, if you like, the optimal speed or velocity for that particular banking. And you can see here it is actually about 36.23 meters a second, or about 130.44 kilometers per hour. Okay, so I mean, after a while you can just jump straight into these formulas, but we're now going to look at the trains, and obviously trains are a particular sort of situation where we don't want to bank the incline too much. The passengers will sort of feel the tilt, I guess you could say. But basically what happens is that when the train starts on an incline, the inner rail, if you read through there, is supporting the weight. And as basically the speed increases, we get to a 0 point which is our optimum speed, if you like, for the train on that particular bank. And then as it increases, well, the outer rail starts to hold the train in, actually, because of the flanges on the wheels. And obviously in different countries you have different basically gauges for rails. They can vary quite dramatically, about 1 point something up nearly to 2 meters. It just depends. Okay, well, let's look at example 3. I'll call it Toot Toot 1, where we have a train traveling around you can see here, a curve of radius about 500 meters, speed 72 kilometers an hour, and the rails are about 1.435 meters apart, which is the Australian gauge. We have a look at we've got to basically find the banking angle and the basically the height h, you can see here, of the outer rail above the inner rail. Now, okay, so how do we do it? Well, we're going to jump in and basically use the expression tan theta equals v squared on gr. Okay. Now, you can see here, this is basically independent of the mass. Okay, so we've got to try and work out, what is our velocity? We've got 72 kilometers an hour. Obviously, we change that to meters per second. Okay, over here, it's about 20 meters a second. And the radius is 500, and then we just put it all into the formula, and then we eventually get that over here somewhere. We've got that. Okay, we need the angle to be about 4.67 degrees, and you can see here the height of the basically the outer rail above the inner rail is about 0.1 1, 2. Okay, just have a quick look up here. This is H. Okay, so it's only about 12 centimeters, not much. Now, trains have got all these suspension things happening in them, and basically it's a lot to do with passenger comfort and stuff. There's a lot in the design of trains and things. Okay, let's have a look at another example. This is a bit of a harder example. Here we are. Now, this is one where, okay, the rails are about 1.5 meters apart. You can see here. Traveling around a bank curve, and the size force on the inner rail at 10 meters a second is equal to the force on the outer rail at 20 meters a second. Find H, the height of the outer rail above the inner rail. Now, we're going to have to basically, you can see here I've got VI for inner and VO for outer, and we basically need to set up the equations. We're going to resolve horizontally and vertically again, and you can see here I've actually set the equations up. Okay, over here. Okay, oops, happened here. Yeah, somehow I jumped off the pen. Okay, alright, here we go. Okay, here we are. Let's set the equations up. And you can see here, NI is the normal direction. You have a quick look over here of the inner rail here, and the outer rail over there. Okay, so the normal inner and the normal outer, okay, we need to obviously basically have a look at the two different rails, okay, so we just basically, obviously the weight's the same, both situations. Okay, alright, so we know these velocities are 10 meters a second and 20 meters a second. Okay, now if we solve for F, okay, now we need to obviously do a bit of work. Okay, we now need to solve these equations for F. Now, that would mean we need to eliminate N from the other equations. I'll just go back and just show you. Okay, so we have N's, so we need to actually multiply them by sines and coses like we did before. But basically, we need to eliminate the N's in both situations, so the inner and outer situation. We get two F's, two friction forces basically, okay, which we can now equate. Okay, so the friction forces you can see there, okay, which we are equating. Now, there was a fair bit of work involved in eliminating, obviously, the N to get the friction expressions. So I'm just going to try and get the pen to work. Let's see if we get the pen to work. Okay, here's the pen. Okay, now, so here, these are the two equations for F. Now, it did work. That's a fairly rough one there, but okay, yeah. So we did get the this is the F. Okay, see for the inner, and you can see here this is the F for the outer, and we equate them, and eventually we get, what do we get down here? You can see here 2g sine theta equals VI, the inner velocity squared, plus the velocity on the outer rail squared cos theta on r, and obviously rearranging that we get an expression for tan theta. Now we know obviously VI and VO and G and R, so we can just basically sub that in and get a value for tan theta, which is about, we can see here, 0.0255. And okay, for small theta, you can see sine theta is approximately equal to theta, which is approximately equal to tan theta. So we can actually find the height. Okay, you can see here we've got the gauge 1.5, and we've got the angle about. You can see here. It's well, I actually didn't. We know that the tan of the angle is actually 0.0255, and you can see over here that the h is actually the sine of the angle, which is approximately equal to the tan of the angle. So we didn't even need to have to work out the angle. You can see, okay, which is roughly, and you can see here that the heights are roughly about 38.3 millimeters. Okay, obviously quite a small amount of basically banking for the train. Well, thank you very much for watching. This has been a long video, and bye for now.